Hello, this is Niall here. Welcome to my presentation on the data analysis and financial feasibility study of our wind farm development site as part of phase 3 of the wind, ocean and hydro energy module. Just going through some of the main points covered here. Firstly, I'll give an intro to the theory that I used in the calculations. Then I will give a breakdown of the wind resource data analysis. Then go through the wind turbine selection. Based on that, then calculate the energy yield prediction. Then I will show the proposed wind farm layout, and then finally just give a breakdown of the financial analysis, and then just give some references that I used. I just removed my camera there because I think I'm blocking an equation. But the main equations I used here in the calculations, firstly to get the scaled up pressure and temperature at the hub height. Then based on that, the density. Using that density, then I calculated the power in the wind using this equation. And to scale up the velocity, I used this log law relationship. To fit the Weibull distribution, I use this probability density function and cumulative distribution function. Similarly, for the monthly max wind speeds, I fitted a Gumbel distribution to it using these two equations. These are just some of the parameters for the Gumbel distribution, and this then is the equation used to calculate the annual yield in kilowatt hours. This is just a nomenclature showing the different symbols used. So I chose to use Python just due to personal preference here. Just for this presentation, just to keep it within time constraint, I can't go into as much detail as I'd like on the code. So I've attached just a separate video with a kind of deeper description of each of the lines of the code. But just here, so the packages that I used mainly for this were Pandas, NumPy, and Matplotlib. So the structure of this analysis will be quite different to the analysis in Excel. So what I'm doing here, just on the right, is just listing the files, so the locations where the data is on my computer, and then each of these lines here just executes a function here which reads Excel files and stores values in a particular column in these data frame DF objects, as I refer to them sometimes. So just after inspecting the data initially, there were some outlying points, as you can see here. So I created a function that takes in a condition. For example, if the points are less than 0 and it sets them to NaN, this stands for not a number. It's basically an empty data type. It's as if the data point wasn't there. I wrote a function here to plot two arbitrary data sets on top of each other. Then I called that function, as you can see here, inputting the site and the met station data. So you can see there's a very close relationship between the data. Based on that, then a year of data should be sufficient because the met mast data is reasonably similar, and that goes back 18 years. The first step for calculating the power in the wind here is to select a hub height. So I selected 90 meters here just based on current industry standards. I've used the log law that I showed earlier to scale the data. So this here is just a function implementing that. And this function can be called with any value of the parameters, and it will return the desired velocities. So I've called it here for the site data. I got the average then of the met station pressures and temperatures, and I scaled them up to the hub height to predict the air density using the equations that I showed earlier. Next, I calculated the frequency of occurrence and the probability frequency distribution using the function in the top right here. So this splits the data up into bins. The histogram function returns the bin edges and the number of instances per bin. Then I calculated the probability associated with the middle point in the bin. And then I plotted the histogram using a separate function that I defined here in the bottom. So the line in the bottom then just calls this function and gives it inputs of specific data, bin size, and whether or not to plot. So when the code runs as well, the functions themselves don't do anything. They need to be called with inputs for each of the parameters like I've done at the bottom here. To fit the Weibull distribution to the data then, I wrote two functions. Firstly, to generate the cumulative frequency distribution, Note that as well that I've plotted the points from the end of the bin because it's the probability that the data will exceed a particular bin. So I've called this function then inside in the Weibull parameter function, and then I performed a sequence of operations to convert it to linear format here. Then plotted this line against the data. So this function here calculates and outputs the coefficients of that line of best fit. This here is just executing that function with the wind speed data. So there looks to be a reasonably good fit of the data to a Weibull distribution here, and the parameters are shown on the screen as well. Using these parameters then, I just overlaid the Weibull probability frequency distribution from the probability frequency distribution from the data, and it showed a reasonably good fit, but it's slightly skewed to the left. I created a function here to calculate the power per unit area in the wind using the equations from earlier. This came out at 814.97 watts per meter squared. Afterwards then I did the same thing to get a value associated with the Weibull distribution, where there appeared to be a 90% difference. So this could come down to uncertainty in the wind speed measurements, just noting that any uncertainty in the wind speed will be cubed for the power. So that could provide a potential explanation. For the wind direction then, I set up bins and calculated the probabilities similar to the previous histograms. I describe all this in more detail in the code breakdown video, but essentially I did a bit of gymnastics here to get an array which contains the velocity values in each bin. Then I calculated the power in each bin using those velocity averages. I made a function as well that I'll show on the next slide that creates the wind rose plots just because I didn't want to repeat too much code. So this is the function here on the bottom right that generates the rose plots. So looking at the three plots, the southwesterly direction seems to be more prominent in the power and wind speed. So I'll be taking that into account later when designing the layout. I created three functions here. The first one calculates and returns the monthly max wind velocities. The second one here calculates and plots the Gumbel distribution, and thirdly, this calculates the reference velocity for the wind turbine classification. So just quickly to get the monthly max speed, I just looped over every year and month in the dataset. I gathered the wind speeds and then returned the max. I then filled up an array of the monthly maxes, which I'll show in a few slides. Just showing the actual execution of the functions then. So I used the Met station data and scaled it up to the hub height. There were some months that had corrupted data just from inspection, so I just manually excluded those, as you can see below here. The extra corrupted data as well is just a function of the fact that the Met station data is 18 years versus just 1 year for the site data. But the Gumbel distribution looks to be a reasonable fit aside from one particular bin. The outputted reference wind speed here is 40.42 seconds. So as I mentioned, I just outputted monthly max speeds to an Excel spreadsheet from Python. So you can see as well the effect here of setting the data points to NaN values, so they're just empty cells really. I used the standard deviation data from the site as well to determine the letter classification. Initially I did this with the 58 meter data, so I ran into some difficulty finding a kind of universally agreed upon law to scale the standard deviation to hub height. One source that I've just listed down here stated that the turbulence intensity is a function of the non-dimensional height relative to the surface roughness. So those weren't values that I felt like I was able to estimate with a large amount of certainty. So I use a slightly different approach based on the available data. So the function here just calculates the proportion of data that's under each of the limits and then generates the plot on the left here. I ended up rerunning that function for different heights in Python. I manually filled out this table then, and just out of curiosity, I plotted it. And there looked to be a linear relationship between the hub height and the percentage of the standard distribution below the class limits for each of the limits. It had an R squared value of over 0.99. So I've made an assumption here that extrapolating these relationships here up to a hub height of 90 meters is valid. Using that then, I predicted that 99% of the data will be below the class B limit. Using the conclusion then on the last slide, as well as the reference velocity, I selected the 2B criteria or the class. So there's obviously some uncertainty in both of the measurements, but they both fall reasonably well below the cutoff points for each of the categories. For the turbines then, I just chose three of the most common turbines in and around the 2B class. So I ended up selecting the Siemens turbine because it had a lower rated wind speed and cut-in speed. And going back to our probability distribution function, that's favorable for our data because we had a lot of data points in the lower wind speed ranges. So this then is just the power curve for that turbine. I scaled this up from a density of 1.225 meters or kilograms per meter squared that was provided from Siemens. Using this power curve then, I wrote a function just to multiply the power values by the Weibull distribution. As you can see here, this outputted the annual and max possible yield, so that gave a load factor of 47.88%. This here then is the final proposed wind farm layout. The yellow circles represent 4 times of the diameter, which is the cross-stream criteria that I'm using here, and the red circles just demonstrate that each row maintains 6 times the diameter spacing, which is the criteria I'm using. So in this case here, the turbines would be centered in the middle of the yellow circles. The setback limitations, as you can see here, they reduced the number of turbines I could fit. I ended up with 33 turbines and a total power rating of 75.9 megawatts. The grid then uses a staggered layout based on the prevailing power direction from earlier. So that's the main difference from the phase 2 layout, which are the blue circles, if you can see them under here. They don't really follow any similar layout. Then just overlaying the same circles on the last slide on a contour of the region, you can see that some of the turbines here are on high land. They're away from the peak, so I've still included them, but they could potentially end up being unfeasible. It's also worth noting that the turbines here were intentionally placed upstream of the mountain, so that the vast majority of these turbines should be completely unaffected by the wake from the high altitude here. For the financial analysis then, I used information from the following sources here for the cost breakdown and losses separately. So these are based on industry representative cases for a very similar size wind farm to the one being considered here. These values are given in euros per megawatt. So I just upscaled them to the wind farm size that I showed. This then is the cost breakdown and the annual energy production based on the per megawatt values in the previous slide. So the calculations here resulted in a capacity factor of 32.94%. So this is in the same ballpark as Ireland's average. And it's worth noting as well that the losses that I've listed here assume that the dispatch down from last year will remain constant indefinitely, which is definitely not guaranteed. So there is some uncertainty in these values. I've calculated the levelized cost of energy using the equations here. That came out as 35.81 euros per megawatt hour. I've also calculated the estimated yearly revenue using electricity prices from this year, averages to date this year. So these electricity prices are very volatile, so it's not a very reliable long-term value, but regardless, that came out as over €28 million. It's also worth noting as well that the levelized cost of energy is just an initial estimate based on the assumptions that I've shown in the last slide. This price as well, or whatever price is agreed upon at the res auction, that will be guaranteed for the entire term of the grant. So in 2022, that grant was 17.5 years, I believe. I've compared the levelized cost of energy that I showed in the last slides to European auction prices from last year. And it appears to be at least in the same range as these published prices. So I think because of that, it should serve as a sufficient initial estimate. Then here, yeah, it's just some simple payback period calculations here. So just dividing the total capital cost by the yearly income, that gives a period of 5.71 years, a payback period. That is a 17.5% yearly rate of return and a 350% lifetime return on investment. Then just some further considerations financially. So the Donegal site is roughly 22 kilometers from the nearest 110 kilovolt connection point and 6 kilometers from the nearest 38 kilovolt substation. The grid connection here then has the potential to significantly increase the cost. So two options of operating the 38 kilovolt station or connecting to the 110 kilovolt line should be weighed up. I just listed the sources that I used here, but apart from that, that's the end of my presentation, so I'll leave it there. Thank you for your attention. I'll just append to this one quick run through of the Python script, and then I recommend watching the more detailed breakdown of the code. Thank you.